Okay, so the next talk is remote. It is about probabilistic programming with vectorized programmable inference.
Hi everyone, my name is McCoy Becker. I'm a student at MIT's Probabilistic Computing Project advised by Vikash Mansinghka, and today I'll be presenting a language designed towards faster, more parallel programmable probabilistic inference. Probabilistic programming languages aim to support practitioners of probabilistic modeling and inference. These systems provide automation to help users write and work with probability distributions. One key operation in probabilistic modeling is conditioning a probability distribution, an operation fundamental to Bayesian inference, a model of reasoning that is commonly used in machine learning and reasoning under uncertainty. To support computing with conditional distributions, probabilistic programming languages provide two key capabilities. The first capability is the ability to describe joint probability distributions, which probabilistic programming languages automate by providing expressive modeling languages. Using these modeling languages, users can write down probability distributions as programs, which often make use of programmatic components like 3D renders, symbolic planners, or program interpreters as part of their definition. The second capability PPLs provide is inference libraries, and automation to support the programming of inference algorithms. These algorithms are programs designed to compute or produce approximations to the conditional distributions induced on the programs written in the modeling languages when we condition those programs on data. Now, in this talk, I'll be presenting a design towards vectorizing the modeling and inference stack for probabilistic programming languages, granting access to good performance and scaling via parallelization. Our concern in this talk is exploiting embarrassingly parallel subroutines in programmable inference. Programmable inference is a paradigm for probabilistic programming languages where users are allowed to customize their inference algorithms, often with degrees of freedom which themselves are programs. Take importance sampling as an example. Importance sampling is an approximate inference algorithm which involves a guess-and-check style pattern, where guesses from one distribution are used to approximate another typically intractable distribution. Here, the target, the imagined intractable distribution, is shown in orange. The programmable inference part is a proposal distribution, which is called proposal in each of the code snippets. This is a programmatic component which is sampled within importance sampling to produce the guesses. These samples are shown in blue on the left-hand side and green on the right-hand side. The samples are scored using a quantity called an importance weight, a density ratio between the proposal distribution and the target. In many probabilistic programming languages, importance sampling is written as a sequential program, shown on the left-hand side of the animation. Samples are drawn from the proposal and weighed in a for loop. But both the sampling process and the weighing process perform the same computation in each iteration of the loop. If we could execute this process in parallel, we could produce many samples simultaneously and then weigh them all at the same time. This is shown on the right-hand side. On modern GPU devices, this drastically improves the scaling of this process as the number of samples increases, a useful way to improve the approximation quality of importance sampling. Our design allows users to do exactly that and take advantage of other opportunities for parallelism in programmable inference. We do this by exposing a vectorization transformation called vmap, which composes with probabilistic automation used to write programmable inference algorithms. Vectorization in this context means transforming computations over scalar data or array data to operate on higher ranked arrays. In particular, vmap stands for vectorizing map, applying a function over some axis of array arguments. In our language design, vmap can be applied anywhere in probabilistic programming code. It can be applied to probabilistic programs which are used as models, allowing us to make use of idioms such as independent and identically distributed random variables, as well as repeated invocation of other probabilistic programs as submodels in our modeling toolkit. vmap can also be applied within inference to support repeated sampling idioms like multiple guesses in importance sampling, as we just saw, but also enumeration patterns. Enumeration is a high-quality inference strategy which is expensive in traditional PPLs which implement it using a for loop, but becomes cheap when vectorization is automated. Overall, our work contributes a compiler for our design which integrates with the GenJAX array programming environment, a formal model characterizing how our design works, and an empirical evaluation including micro benchmarks and 2 case studies. Before walking through how our design works, I want to give a short and quick practical survey of the applications of our work. Our system can be used to support probabilistic modeling applications like robot localization. We'll see more about this example near the end of the talk. But quickly here, a robot traverses a 2D geometry world and we get noisy measurements of its position. The goal is to infer the trajectory of the robot. A particularly good programmable inference algorithm class for this type of problem is sequential Monte Carlo, and our system is set up in such a way that we can support several various vectorized versions of this algorithm. In addition, because the implementation of our language and compiler makes use of JAX, a robust and mature machine learning framework, we benefit from great automatic differentiation support, allowing our system to support fast vectorizable Hamiltonian Monte Carlo, a technique commonly used in statistics in PPLs like STAN and NumPyro. Finally, vectorization can be used to take advantage of modeling structure like conditional independence. Our system can be used to exploit conditional independence to parallelize high-dimensional inference problems, drastically reducing the time it takes to execute the inference processes. For instance, we perform approximate probabilistic inversion in a noisy version of Conway's Game of Life for a 512 by 512 game board in milliseconds on a consumer-grade GPU device. Now, for the next part of the talk, I want to give intuition for our design and system works. And quickly, I'll just say that our paper contains a formalization of the intuitive presentation, which I'll give now, with a formal calculus, denotational semantics, and correctness theorems, along with logical relations arguments. I'd refer interested viewers to our paper for the details of our formal exposition. But for the rest of the talk, the examples I will use the syntax of our compiler implementation. The syntax is Python code, and our compiler works by exposing a DSL in Python to users, which allowed them to write our system's probabilistic program type, a type called generative functions. Generative functions are used to denote probabilistic models in our system. And a few things to note about the syntax of generative functions. First is the @gen decorator that you see on lines 2 and 10 above the Python functions denotes that the function is a generative function. Now, within one of these generative functions, users can introduce random choices by invoking distributions, and even other generative functions by using the addressing @ notation, where the addresses are shown in green in the code snippet on the left-hand side. Here in polynomial, for instance, on lines 2 through 7, we define a model over the coefficients of polynomial curves. Each coefficient is drawn from a standard normal distribution. Now, the design of generative functions is compositional. We can use the polynomial program inside of another generative function point to define a bigger distribution over curves and point data. Now, given one of these generative function objects, how can we compute with them? What can we do with it? Our design gives users access to interfaces for probabilistic computation. These interfaces, called the generative function interface, cover concerns like sampling, density evaluation, updating of an existing sample. There are other interfaces as well, which you can see in our full paper. So one applies these interfaces to generative functions to construct probabilistic computations. One can use these interfaces to implement inference algorithms. Take important sampling again, for instance. Programmable inference algorithms often involve logic that requires sampling from one generative function and evaluating the density of another. Here we sample from a proposal using Simulate, which gives us an object called a trace. A trace is a structured sample from a generative function, which I'll talk about in the next few slides. We then use the trace to we then take the trace and evaluate the density of the model generative function at the trace using the assess interface to compute the importance weight for importance sampling. Remember, this is the guess and check strategy for approximating the distribution of model that we saw earlier in the talk. Now, let's dig in a bit more and get a bit more intuition for Simulate and how it works. Simulate samples a trace from the distribution which the generative function denotes, and at the same time computes the evaluation of a density function for the generative function at the sampled trace. Traces in our system hold tree-structured data with addresses and the values of samples along with that density evaluation. The addresses in a trace can be read off from the syntax of the generative function. On the right-hand side, for instance, the point generative function has curve and obs as addresses. And the curve address denotes the invocation of the polynomial generative function, which itself has a, b, and c as addresses. The result of applying simulate to the point generative function is the trace structured on the left-hand side, this hierarchical tree structured object. But just to make it clear, in our point model, a trace represents a curve and a single point sample and a density evaluation. That's all, even though the object has this structured hierarchy. This is what it's representing, a distribution over the data on the left-hand side. So then how are probabilistic interfaces like simulate implemented in our system? Well, they're program transformations. Our compiler takes the source code of the generative function and constructs a transformed representation that accumulates the samples and density values required to implement the semantics of simulate. You can see our paper for a detailed description of how this works, but on the right-hand side we show the first-order representation that our compiler outputs. It consists of sampling statements, array primitives, density evaluation statements. And this same type of structure is true for all of our other probabilistic interfaces. They're all implemented as program transformations. Vectorization also works as a program transformation. It's a trace structure preserving program transformation on the representation I just showed you. The real work of vectorization is done at the primitives of our language. All primitives have built-in vectorized versions. Each primitive has a rule for how vectorization under the vmap transformation transforms it to operate on higher ranked values. Practically, this means that under vmap, computations which produce traces create the same structure, the same address structure, but with vectorized leaf values. Here, for instance, you can see that under vmap, the obs value might be inflated from a scalar to a length 5 vector of floats, depending on how the user wishes to use the vmap transformation. So these interfaces, the probabilistic interfaces and our vmap vectorization interface, give us a model of programmable inference and user-directed vectorization. How does vectorization look in our syntax for our users? Say we want to write a regression model where we define a distribution over multiple points, all drawn noisily from the same curve, the same polynomial, but at different values on the x-axis, which are passed in as arguments to the generative function on line 19. This is the x's argument. To start, we change the signature of our point generative function to accept the coefficients of the polynomial curve as arguments. And then on line 22, we apply vmap to the generative function. We make use of a keyword argument here called argsmapped, which specifies that vmap should be applied over the first argument, that x is the values of the independent variable that we're passing in. Using vmap and that argsmapped keyword argument, we specify that we're mapping over the input x's. We get multiple values for the independent variable. This induces a model which maps over the input x values, a vector of x values, and samples a point for each one. It's a bit easier to understand this visually. If we simulate from the endpoint curve program, that thing that we just defined, we get a trace which represents the type of data that's shown on the left-hand side, a curve and multiple points. This is starting to look like a distribution that could be used for regression. The trace, which includes the random choices and addresses, looks like the right-hand side. It's the same structure as the original trace we started with, the same address structure. But note that obs, which before contained a single scalar random choice, now includes 5 draws for each point. Now, we created that endpoint curve program by applying vmap inside a generative function. We used vmap as a modeling idiom. We applied it to point, another generative function. But our design also allows us to apply vmap to the result of applying simulate itself. Here on this slide, we vmap the application of simulate to our endpoint curve program. Right. So now this is an example of nesting of the vmap transformation. This returns a trace with the same random choice structure as the original, which here we've called traces to indicate that it corresponds to multiple samples from the endpoint curve generative function. Oh, and here we're making use of another keyword argument, repeat, that just means IID samples from the probabilistic computation. Because vectorization is trace structure preserving, nesting of vectorization is handled automatically. What we saw on the previous slides and shown on the left-hand side, when we vmap the point generative function and apply it over, say, 5x values, we inflate the rank and shape of the obs random choices, the obs random choice to an array with length 5. Then on the right-hand side, I'm showing what we just did on the previous slide. When we vmap the application of the simulate interface, the sampling process itself, we get multiple independent samples from that distribution. And I'm showing 3 of those samples on the right-hand side. Note that the coefficient random choices in the vectorized trace from vectorized model have changed rank and shape, and so has the obs random choice, up to an array of size 3, 5 now. In addition, the density for the density is now a vector, each element corresponding to a density evaluation on each of the independent samples. This slide gives intuition for how repeated application or nesting of vectorization works in our system, nesting of our vmap transformation. So that gives a sense of how our system works. We have these probabilistic and vectorization interfaces. But then with these interfaces, one can construct interesting programmable inference algorithms. Here on the left-hand side, I'm showing custom proposal importance sampling, where default proposal is itself a probabilistic program. This is just the same importance sampling recipe that I showed before, expanded out a bit. Now, the thing to note here is that this is a single particle version of importance sampling. But by using vmap, we get a multiple particle version for free, in a sense. On the right-hand side, we're free to apply vmap to the single particle version, and we get out a multiple particle version using the vmap transformation. And the big payoff here is that the big payoff of vectorization here is utilization of parallel hardware to scale algorithms like the one shown on the previous slide and other inference programs. For instance, we might be using our polynomial regression model to infer curves given data, which is shown at the bottom. Using our system gives the user access to GPU execution, and the scaling becomes close to constant until the GPU memory is fully saturated. In the top left figure, we're showing the scaling as we increase the number of guesses in importance sampling. In the top right figure, we're showing the log marginal likelihood estimate computed from the importance weights. This is an estimate of the probability of the data and is used as an informal intuition for goodness of the approximation. Within our language, it is easy to scale inference algorithms, inference programs in embarrassingly parallel directions using vmap. Now, we implement a compiler for our language called GenJAX. Our compiler is embedded in Python, builds on top of JAX, and uses program tracing to lower Python functions to a first-order IR. We saw this when I was discussing how simulate and our other probabilistic interfaces are implemented. Program tracing allows us to partially evaluate away our high-level program transformation automation, and we're left with pure vectorized code in JAX, which can be further compiled with state-of-the-art compilers like XLA to run on GPUs and other pieces of parallel hardware. Moreover, because we closely integrate with JAX, our system can make usage of all of JAX's existing automation, including AD, automatic differentiation for algorithms such as Hamiltonian Monte Carlo. We benchmarked our compiler implementation and found that it is competitive with hand-coded JAX while retaining the benefits of our high-level automation on several modeling and inference tasks using importance sampling and Hamiltonian Monte Carlo. We also explored the capabilities of our system on several examples, several example case studies. One example involves approximately inverting Conway's game of life using Gibbs sampling. The rules of the game of life are shown here. The transition function defines simple evolution rules for what pixels are turned on and off in the board state, given the state of their neighbors. The question here is, given an observed state, determine a preceding state that evolves to generate the observed state. The state space here is huge. For a 512 by 512 board, the number is quite a bit more than the atoms in the universe. We can set up a probabilistic model version of the game of life using generative functions and approximately invert it using inference. A key observation for this problem is that the posterior in the model given a fixed target state of the game of life, can be factorized due to conditional independence due to the transition function. A good strategy here is to sweep across the board by breaking it into pixels with windows which are isolated from one another, flipping those pixels by sampling from each of those local factorized posteriors and repeating the process. This is a Gibbs sampling algorithm, and vectorization allows us to compute the flips for all the windows in parallel. Applying this technique allows us to discover approximate inversions in milliseconds on a GPU, even for a large 512 by 512 board. Another example involves constructing a toy problem in robotics. A robot traverses a world and gets noisy LiDAR-like measurements of its surroundings. If the map is known, can we infer where the robot is within the map? To solve the inference problem in this example, we use a programmable inference algorithm class called sequential Monte Carlo. Sequential Monte Carlo produces a particle approximation to the location of the robot, seen in shaded green and yellow. The standard variant of the algorithm, which is shown on the far left, uses the prior of the model as a proposal. In this case, the prior is random walking with Gaussian noise. This fails to accurately localize the robot, as you can see on the far left side. But there are many variants of SMC. A common technique used to improve the algorithm is to apply MCMC inference moves to the particles at each time step. This is shown in green in the middle, where we use HMC moves to try and improve the approximation. Now, it improves the performance over blue, but loses track of the robot in the middle. A final strategy is to use a custom proposal as a guesser. So instead of using the default proposal, we use a custom one, another program, another generative function as the proposal. On the right-hand side, we make usage of vectorization to enumerate a grid near the current latent position. This grid is weighed according to the observed likelihood of the data, and the maximum on the grid is chosen. From that maximum, we then sample from a 2D normal to guess the next latent position. This strategy is highly efficient and makes usage of vectorization in 2 dimensions, vectorization over particles as well as vectorization over grid points. So this is an example of nested vmap in inference. Now, this variant ends up being the most accurate and the fastest, approximately 2 milliseconds to track the robot accurately over 16 time steps. Now, in conclusion, we've discussed our work on a compositional approach to vectorization of programmable inference. We refer interested viewers to our paper where we give a careful treatment of our formal model and discuss other features of our system not covered in this talk. Thank you for your time. The QR code on this slide provides a link to our system implementation and POPL artifact, and please send any questions to my email. Thank you again.